So let's look at Dido's problem, where what we had to essentially minimize was this, yeah, and subject to a constraint, isn't it? This was the length of the ox hide which Dido was to use for carving out a largest possible area along the coast. Okay. So, if I call this as my L and this as M, then let's look at L hat is equal to L plus lambda M. See, the beautiful thing about this is when this constraint is met, yeah, what happens to the cost value? Because that other part ceases to matter, no? So that's why it's tantamount to minimizing whether you do L hat or L, it doesn't make a difference. Okay. So do you see immediately that this boils down to y plus lambda square root 1 plus y prime squared. You might say, what happens to this c here? If you don't like this, just call this equal to c and just treat the part within the integral, because remember we already said we are only treating integral constraints. The parts that are outside the integral don't matter. Whether you set this to 0 or some constant, it will not matter. Okay. Alright. Now, what does this immediately suggest to you? What should you invoke here? Should you just blindly apply the Euler-Lagrange condition on this, or is there some simplification that you can do, some special case perhaps? Which situation are we here in? No x situation. So in the no x situation, what remains constant? The Hamiltonian, which is y prime into L y prime, which is the partial of L with respect to y prime, minus L. Okay. So let's try and look at this. So y prime into L hat y prime minus L hat. What is that going to be? Help me with this. This part with respect to y prime doesn't matter. This part you will just have a 2y prime and a half with this in the denominator. So the 2 and the half cancel each other out and you are left with lambda y prime, right? So y prime times lambda y prime upon square root of 1 plus y prime squared. Agreed? I hope I am not making a mistake here. So please be on the top of your game. This will help you score marks in your exams, because you have to be good at integrating and solving differential equations. That's the essential part. Okay. So this is L y prime dot product with y prime minus L. What's L? Well, that is y plus lambda square root 1 plus y prime squared. What is this got to be equal to? Some constant, right? So essentially this is equal to some constant, say k. This implies lambda y prime squared upon root 1 plus y prime squared minus lambda into 1 plus y prime squared divided by root 1 plus y prime squared minus y is equal to k. Or I can just put this y on the other side is equal to y plus k, right? I hope that's all right. Please check and stop me if you find any mistakes here. So what happens? This gets cancelled. The lambda y prime squared and lambda y prime squared get cancelled here. So what you're left with is just minus lambda divided by square root 1 plus y prime squared is equal to y plus k, which means I'll have root 1 plus y prime squared is equal to minus lambda by y plus k. If I square this on both sides, I get y prime squared is equal to lambda squared minus y plus k whole squared divided by y plus k whole squared. Of course, you can take the square root, you will get plus and minus both of them. You will have to keep one and discard the other, right? So what happens? This is now about time we got this in its proper form, which is dy dx. So all y related terms you get on one side and the x related term you get on the other side. So what happens then? Y prime is equal to square root of lambda squared minus y plus k whole squared upon y plus k. So let's just replace this y prime with dy dx, which means you have y plus k dy upon square root of lambda squared minus y plus k. You can keep the plus or minus sign here, by the way, on this outside of this radical. As we shall see shortly, it will not matter, but if you are a stickler, you can do that. So this is integration dx. Yes? What should we do now? Any suggestions on how to carry out this integration now? Substitute what? Substitute the entire thing inside the radical as get rid of the radical. No, that's the fundamental idea. So call this p squared. Yeah. So put lambda squared minus y plus k whole squared is equal to p squared, so that 2p dp is equal to minus 2 y plus k dy. The 2 goes chop chop. So you are left with whatever is on the denominator is just minus p dp. Yeah. So you have integration minus p dp, and what's here? Just p. It gets cancelled, right? So this is dx, which essentially means that x plus some k bar is equal to p is just this fellow, right? Plus minus square root of this. Yeah, that's why I said the plus minus of that will not matter, right? So at this point I can actually safely put the plus minus without fear of missing out anything. Actually I could have kept the plus minus earlier also. It doesn't matter. Okay. So what is this? Radical of lambda squared minus y plus k whole squared. So you square it on both sides and what do you have? Equation of a circle. Exactly. Like we had said would be the case earlier. Of course, those terminal conditions and everything will decide the radius of the circle, where it will pass through and so on and so forth. But essentially it's nothing but x plus k bar whole squared plus y plus k whole squared is equal to lambda squared. So there you have the solution of Dido's problem using the Euler-Lagrange condition on a constrained optimization problem. Yes, we have to account for the constraint as well, which is the length of the ox hide that she should have used to carve out her territory. Okay. So we will end this today with the other problem that we had discussed earlier, which is the catenary, and show you exactly similar sequence of steps. Only thing that you need is a bit of skill with integrations. Okay. So let's also get a bit of practice and warm up. This, as I said, this also doubles up as sort of a tutorial session in some sense, right? Because the problems we've given you in your sheet would require you to every now and then use integration and be good at it. So get some warm up and practice on this. Let's look at the final problem for this lecture, which is the catenary. Once again, the form of M is the same. If you recall, in the catenary, again it was the length of the cable or the chain that was constrained. The only difference between the Dido's problem and the catenary is in the cost function. In one you are trying to maximize the area, that's in Dido's problem, and here if you recall we had this. This was the potential energy, right? Integrated over. Yeah. Okay. So in this case our L hat, remember M is same as before. So our L hat will be y square root 1 plus y prime squared plus lambda times square root 1 plus y prime squared. And once again, what do we see here? Is this a special case? Or do we have to apply the whole Euler-Lagrange nasty expression? It's a special case, isn't it? Again, there is no x here. So once again, we can say that the Hamiltonian, when it's cooked up using L hat instead of L, the Hamiltonian needs to remain constant, and subject to that we have to solve a differential equation, right? So this is actually y plus lambda times square root 1 plus y prime squared. So let's see what is y prime dot L hat y prime minus L hat. What is this? Y prime dot the partial of this, the y plus lambda remains untouched. This one pulls out a 2y prime outside, but again gets cancelled with the half. So you have y prime y square root 1 plus y prime squared. Yes, I hope not making a mistake here. Minus, sorry? Oh yeah, yes, thank you. See, I was making a mistake. Okay, good, y plus lambda. Thank you. Yeah, now it's correct. Minus this, which is y plus lambda times 1 plus y prime squared. And this has to be a constant now. Let's call this k as before. So what do we do here? Again, take the denominator common. And of course, y plus lambda is also common. Y plus lambda is also common. What else? Y prime squared minus 1 minus y prime squared. So that's just a minus 1, isn't it? Yes? So it's just a minus sign. Sure? Agreed? And that's going to be equal to k, which means that you have k, or rather y plus lambda by k with a minus sign is equal to 1 plus y prime squared Now you square both sides. So you get y plus lambda whole squared upon k squared is equal to 1 plus y prime squared. Once again, take the 1 on the other side, subtract 1 from both sides. So you get y plus lambda whole squared minus k squared divided by k squared is equal to dy dx whole squared, right. So now again the radical will come in with a plus or a minus sign. So dy dx is equal to square root of y plus lambda whole squared minus k squared, which means, of course, you can take a plus or a minus sign, dy by square root of y plus lambda whole squared minus k squared is equal to minus dx over k. What does this imply? Anyone remembers this integration? Sorry? Some hyperbolic functions inverse. Of course, you can always put those trigonometric substitutions, yeah, and call this y plus lambda by k as sec theta, and you will get in terms of logarithms. But then if you remember, hyperbolic functions were after all just representable in terms of exponentials, right? The sine hyperbolic is just, you know, e to the x minus e to the minus x by 2. The cos hyperbolic is e to the x plus e to the minus x by 2. So eventually you will get there. But if you remember your relations, you will immediately see that this is nothing but the cos hyperbolic inverse of what? Of y plus lambda by k. Yeah. So this is cos hyperbolic inverse of y plus lambda by k is equal to, again you can just take the plus or minus of x with respect to this, it really matters not here, x plus some constant of integration will arrive here. For want of a better term, let us just call this whatever you want, gamma by k. Yeah, gamma by k is the constant of integration, so you can just adjust it accordingly. Yeah, plus or minus. So this tells you what exactly? That if you now take the inverse mapping on both sides, you will get y is equal to cos hyperbolic. Why did I say that this plus or minus sign won't matter? Cos hyperbolic is a, right, it's an even function, right? It's e to the x plus e to the minus x. So whether you take this plus or minus, it really won't matter. So you can just as well say this is x plus lambda upon k with a k appearing here as well, I believe, minus lambda. So x plus gamma by k minus lambda. So that's the equation of a catenary up to some shift in the x direction and the y direction, which is obviously going to be dictated by your terminal constraints. Okay. So we've already seen not just the fact that this idea of Lagrange multipliers can be extended to our calculus of variation settings, but also it can be used to good effect provided you make that mental transition from L to L hat by accounting for this lambda times the constraint. Of course, the restriction still remains that the constraint is an integral type constraint. Quite often, see, integral type constraints, as I had said earlier also, are pathwise constraints. It's something that's telling you about the entire path, something that's true, the entire length is fixed. Quite often the constraints may not be given in that form. Constraints may be pointwise constraints. Yeah. So suppose you want to meet certain or you want to optimize certain cost, but at the same time you don't want, say for instance, the curve to be too steep at any point, okay, or at some point you want the curve to bend in a certain fashion. So then you will be required to give a constraint in terms of the point, right. So integral constraints are not the only kind of constraints that you will have to deal with when delving into calculus of variations and finding out these extrema or these extremal functions, right. You might be also required to, you might be also called on to solve for constraints that are not necessarily integral. In such cases, what do you do? That is what we shall look at in the next lecture. The idea that I want to give you a hint towards is this: so far these lambdas are constants. Now you are saying that, okay, I am not saying something about the entire path, I am just saying something about certain points on the path. So it is like some point-wise constraints. So perhaps if I just allow this lambda to vary with x instead of staying constant throughout, that would solve the issue. And that is exactly what we shall see next, that when you have constraints that are not of the integral form, you can still accommodate for them within this framework by just making the tweak whereby the lambda is no longer some constant number but also a function of x. Lambda varies point-wise accordingly and shapes your constraint thereby. Okay. So that is what we shall see in the next lecture, day after tomorrow. Thank you.